Welcome to your review for the first energy test. So to start off, our patterns, they always look like this, right? I've given you the general equations, so you had a general idea. I want general things up here and then specific equations down here. So the specific equation for 1/2 mv squared, in this case our mass is 4. So the specific equation would be 1/2 times 4 times v squared. So as we go down, we're going to plug in v, right? Each time we're plugging in v. So when v is 1, we've got a total EK of 2. When v is 2 squared is 4 times 2 is 8. And 5 squared is 25 times 2 is 50, right? And if you want to set that up kind of like I was shorthanding, you can also do an equals, what is 1/2 of 4? 2 v squared, right? This is the exact same thing. It's not any different. And then, of course, you'll graph it. We got to pick our biggest value, put it here, and then spread it down. Biggest value, put it here, spread it down. And we'll get this quadratic curve. So the second one, general equation is Mgh. Specific equation involves plugging those things in. What's our M? 30. What's our G? It is always 10. G equals 10 every single time, unless we go to Mars. And our H is what we're going to be solving for. So 30 times 10 times H, we put these in, so we get 300, 600, and 1500. So then we'll graph it, right? 1500's got to be up here, 5's got to be here. We spread it, divided by 5 makes these 300 each. And this is 1, 2, 3, 4, 5, and we'll get a nice linear pattern this time. So that's what we write here, right? Linear and quadratic. Crucial difference. Our gravitational potential energy depends linearly on our height. Kinetic energy depends quadratically on our velocity. Both depend on mass. Mass will change both of these. All right, so over here we got the total energy, our general equation. I didn't put that in for you. General equation is all the energies added up. Energy total is all the energies added up. So EK plus EG. We're going to add them up. So specifically, we've got ET. What is EK? We've got an equation for that. Well, it's right over here. We got to get in really good habits about looking for those letters elsewhere on the page. So EK is 1/2 mv squared. What's our m here? 6 times, what's our v here? 0 squared. Plus, what's our E total? EG, Mgh, right? So let's see, our M is 6, our G is 10 as always, and our H is also 10. So what is our E total? And why did I go ahead and put all these variables in? Well, because H, right, we're putting the starting energy. So the energy total is 600, and that makes this 600 the whole way down. Our energy total does not change. We've talked about this in literally every class period. It's very important to recognize that our energy total does not change. So we just get a flat line. Let's say I put 200, 300, 400, 600, flat line. You can do anything you want for the scale over here because it's just going to be a flat line. So what I set this up for is to set this up. Same situation. EGP is specifically Mgh. EK is specifically 1/2 mv squared. So we take these totals and we enter them in here, and we know that that's got to be the total. We can solve for the EGP each time. EGP equals Mgh. So mass of 6, G of always 10, and then we've got these different H's. So the H's now, we are going to get different values. So we put 5 in here, we get 300. Put 2 in here, we get 120. 1 in here is just 60. What's our EK? Well, it's the leftover. 600 minus 300, there's got to be 300 of EK. That's the only way this can work, because the E total is the 2 added up. Remember, go look on the page for other areas where you see what you're looking for, and you might be able to find it. So this should be 480, and this should be 540. And so when we graph EGP Again, we go to our biggest value, 300. Biggest value over here, 300. Divided by 5 is 60 each. And when we graph this, we're actually going to get an inverse line here. So our pattern here is constant. And our pattern here is negative linear. It's not inverse, actually, because it's not the curve, but it is negative linear. When we fill in the in-words section, we always have a very specific formula. When the independent variable increases, the dependent variable does something. It's always kind of our pattern that we talk about this with. So for this one, it would be when the v, right? When the velocity increases, the ek increases quadratically. We want to add that idea. It doesn't just increase, it increases quadratically. So I don't want to write out all of these, but linear has a very specific relationship. Constant, again, it needs to be when our independent variable, when height increases, what happens to our total energy? Or in fact, in this case, it's decreases in our table. But as long as you're consistent, you can do increases. Once we have it in a graph, we can look at it increases. What happens to the ET? Stays the same. And then for this one, I do want to clarify that this is when an object is falling. Because otherwise, this pattern will not always be true. But when an object is falling, as the gravitational potential energy increases, the kinetic energy will decrease. As this one goes up, this one's actually going down. And these four ideas, these four sentences are really crucial because that's the whole thing that we've been doing. When the velocity increases, the kinetic energy increases quadratically. When the height increases, the gravitational potential energy increases. That's a crucial idea. When the height increases or the kinetic energy increases or anything else, the total energy stays the same. ET stays the same. It's a crucial idea. And then when an object is falling, our gravitational potential, as the gravitational potential goes down, the kinetic energy goes up, or you can say it the other way, as the gravitational potential energy goes up, the kinetic goes down. And so these are the two situations where if we throw something up in the air, it has lots of kinetic at the beginning, and that kinetic gets smaller and smaller as the gravitational potential energy gets bigger and bigger. In the reverse, when we drop something, we drop it with a lot of gravitational potential energy, and as it falls, it gets less and less gravitational potential energy, more and more kinetic energy. That's the idea here. So when we're comparing these, the total energy for ball falling pattern describes what's happening to the gravitational potential energy and the kinetic energy as the ball falls. Well, gravitational potential energy is dropping as the kinetic energy increases. The gravitational potential energy is turning into kinetic energy. So direct transfer.